Hello, my name is Scott Mezgian, and today I'll be doing problem 35 for week 9's first explainer video. Figure P21.35 shows a heat engine going through one cycle. The gas is diatomic. The masses are such that when the pin is removed in steps 3 and 6, the piston does not move. So then it asks us to draw the PV diagram, asks us how much work is done per cycle, and asks us the thermal efficiency. So quickly, let's just draw the PV diagram because I think that's quite easy. So here we'll start just with kind of a rough graph, P and V, and then notice that we have 1 ATM, so we'll start with, and this is an ATM, and then we also have a 3, so we'll mark that, and then we have 50 centimeters and 100 centimeters, and that's kind of it for the volumes, so we'll mark those as well. Alright, so now we know at step 1, it's at 50 and 1, so that's the first point. At 2, it goes to 3 ATMs, but the same volume. Um, at 3, we now get more volume, so that's here. At 4, it's kind of the same. At 5, we cool to 1 ATM, same volume. So far we've gone like this. And then lastly, we cool down to 50 centimeters cubed. So that's the PV diagram quite simply. And then what we can do after we've done the PV diagram is we can try to see the work done. So this is A, and that's done. So for B, we want to see the amount of work done. Uh, really, all you need to do for this part is just calculate the area under the curves. Obviously, these lines are straight up and down, so you can't really calculate work from that. Um, and remember that you got to subtract the negative work done. So in this, since the arrow's going in the positive direction, that's positive work. But then this arrow is going towards the negative direction, so that's negative work. So really, you only need to take the area from inside this box. So let's see. So that is 3 to 1. So that's you know that's 2 here. And then this is from 50 to 100. This should be cubed, sorry. And that is just 50. So then you can convert ATM to pascals and centimeters cubed to meters cubed, and then you'll get about 10 joules if you just multiply them together after converting units. Pretty simple. For part C, um, efficiency. So yeah, efficiency, if you recall, it's just the work you put in, I believe. No, sorry, the work you get out over the work you put in. So work out versus work in, and that is Tonito's definition of it. But really, that in equation form, that just looks like actually the workout over QH for a heat engine. And so we already know the workout, that's 10 joules, so perfect, halfway done, right? QH is a little bit complicated. Um, all it is you sum up the heats when you're heating up. So like if you remember how like the isothermal curves work, they're kind of like this. So this will be one temperature, another temperature, and um, so we know that from here to here, that would be an increase in temperature, and from here to here, that would be another increase in temperature. From this dot to this dot, that would be a decrease, and then same for this dot to this dot. So we'll only calculate basically from step 1 to step 2, and from 2 to 3. That'll be what we're calculating for QH. And if you look in the book, it'll tell you that um, QH for an isobaric and isochoric process are NCP slash V triangle T. And for CP, that's just 7 over 2R for diatomic gases and 5 over 2R for V. Basically, calculate these, add them together for both processes for 1 to 2 and 2 to 3, and then you'll get your final answer after plugging that into the work. And so that gives you a final efficiency of, I got 23%. And also, just a quick note, uh, for help in this problem, I found it really useful to look at page, what was it, 579. There is a really good problem that is good to help you if you're still confused. But yeah, that's all I have for you. Thank you for watching. Have a nice day.